Hello, this is Professor Mike Labasi for St. Clair Community College, and this is for my CIS 2808 Digital Forensics course. And this is a look at Module 4 for our new CHFI, Computer Hacking Forensics Investigator series. This is in Volume 1, Chapter 4. And this is, of course, off our new the EC Council CHFI material. And this usually is around week 4, but this is called Topic 4. Data acquisition and duplication. So I'm not going to go through the entire textbook, of course, and I'm just going to do a quick demo and talk about some of the key things from the chapter. The chapter has got some good stuff. We have a lot of information inside here, Module 4 itself. So first off, again, please review the whole chapter. I've noticed a lot of the material will have really good concepts up front and have more a step-by-step or a tool review or some methodology review in the later areas, like example, preparation for image, filing, and examination. Good stuff here. Again, it has scenarios, it has command lines. It's great, so definitely good for reference, also review. But we're going to focus more on the beginning of the chapter and some of the areas here that data acquisition itself is very important. I think is important to look at. So again, for topic 4 here, we're looking at module 4. And this is probably one of the most critical concepts. I think I say that a lot. This is definitely one of the critical concepts we have in digital forensics. Whether you're using a phone, a USB drive, a computer, a hard disk from a computer, things like that, any improper acquisition and handling of the evidence may render it admissible in court. So this is a huge process, and there are some really good references besides the textbook I will refer to in a minute here. But we will look at live acquisition and dead acquisition. So basically, two ways to look at how you acquire data. Basically, it's a powered off or powered on. It's a system. So that might change your approach to how you might do this. For live, there is something called the order of volatility here. And the textbook talks about it here. So if it is really critical and you have time, so one of the things we're going to look at here is time and tools. But there's some other ways you can acquire evidence if time is of sort of the essence. This is a lengthy process because the way the copying happens is basically bit by bit. So you can imagine today with even in the future from this video, we're getting larger and larger hard drives. Complete hard drive images for 1 terabyte drive could take hours. So there are other ways to do that, but also it could depend upon what evidence you need to have. So again, we have, of course, this on this page here talks about the order of volatility here. There's guidelines for evidence on registers, process cache, routing tables, kernel stats, things like that, temporary file systems. So these are definitely going to be while the computer's on. And you can always collect that with third-party tools off of removable media. So it's very important to look at that. We're going to focus more on the acquisition. Probably going to look at more at acquiring the image from a disk. So that's here, disk or storage of the media. This is probably the bigger ones right here. Most things have, of course, let me go and highlight that. Most things here really refer to, we have drives. Whether you have a smartphone, a laptop, or a server, desktop, you name it. Even IoT devices might have some sort of written cache to a drive somewhere. So that's probably going to be the largest thing. And how you collect it's going to take various shapes and forms. Also, we have remote logging. So this is something you think about too. Again, computers today aren't just in a silo or air gapped. Very, very, very rare now. Your phone itself might have evidence on other remote systems, remote logging, what that device has touched. So this is the concept we talked about earlier, but keep that in mind. Cloud storage is a huge one, and backups. So if a perpetrator or a suspect has destroyed the evidence, it's possible you might be able to get enough information to see from network traffic that they have a written backup to an Amazon S3 bucket. So that could be, you could get a proper warrant or search and seizure where you need to have and gather that information from Amazon. So network topology, things like that. So you can see here as you go down here, and we'll look at acquisition. So very important here, order volatility. Again, registers cache. So we can approach this based off what the system state is in, what access you have to that system, and what evidence you need. Um, so the biggest things here is this. You do not work on the original evidence. And when you capture this evidence, you usually use some sort of read-only methodology, read-only channel, if at all possible. Use clean media to store your copy, and then you'll verify the integrity of this media. So um, this is very critical, and clean media. So you also will verify the integrity of your clean media. So you will zero out, you'll have probably a stack of drives, large capacity drives that all have been zeroed out using a valid process to zero the media up or clean it, verify it with something like an MD5, verify the clean media, and then verify it afterwards. So you know what a clean media looks like, and you can check that. But you always do this. You always create a copy, and you use the copy. You create copies of that. So you never really touch the original. You keep it as read only. So there's a lot there to that. We'll take a look at that. So there are other ways to do this, of course. I talked about time being of the essence. Normally, it's a bit by bit copy. Large system require a lot more time. But if at all possible, you need all aspects of that drive. That's probably this is the best you can get. And we'll look at an example of that. But you can also use a read-only and capture certain files or file types. So for example here, if you're only looking for email, maybe it's an email-only social media, so maybe a social engineering attack, and you're trying to collect evidence on that. It's possible just to get the files you think are needed, like Outlook files, for example, or certain records from a server. Example, log files are probably the biggest ones. So it's possible maybe to collect just those log files and use those to get the most pointed evidence for the case. So again, this could be sparse, so we have sparse acquisition is possible to logical acquisition, which is this fragment. So just the home directory, for example. So and in C users user Mike, you just grab that users. Now again, if we think the user is very well adept to computers, maybe doing anti-forensics techniques, which we'll look at that later, you might need to collect more, but you can start with more sparse acquisition. So again, bit by bit copy. We'll look at that. The text talks about that a lot, and we'll look at some tools here for that. So one of the biggest tools we'll look at is called DD. We actually have that running right now, and it's probably running, still running. I'm running Windows 10. This is the lab, still running. So we'll come back and look at that. DD is one of the standards. I think it's data duplicator, DD. This is a bit-by-bit copy that's used. Now there are other ways to do this. We'll look at that in a second. There's one called dcfldd, which is Department of Defense Forensics Labs DD tool, and it does some things like hashing on the fly, which is great. But we'll look at this in a quick demo here in a second. But in our other guidelines here, like the forensics examination of digital evidence, this is from the Department of Justice. It also will talk about in their section here that ensure the evidence is forensically clean. Let's go and clear that out. So forensically clean when acquired. A write protection should be initiated. This is really important. You want to make sure you don't write back to the evidence. If it's been altered in any way, it could be inadmissible in court. And that is a huge, huge issue. And that's something that defense will look for. And it makes sense. You don't want to allow tampered evidence. And this can also be for the not just preservation for defense. You don't want someone mess with the evidence to cause issues. That is allowed. You can see where that can be some issues. So with these write protected devices that have been used now, with these online labs for this course, we don't really have those, but we'll take a look at them. But write protection is really huge. So also this hardware that should be gathered should be verified, tagged. It should also be tested. This is part of the lab setup. Any kind of forensics lab will have this process. You might actually have a tool division that will look at tool updates, tool testing, things like that. If the tool has not been updated, if it hasn't been verified, if it's shown that it's not working correctly, that tool can be brought in and shown, because even though we think it has been a write only, it didn't work. It brings in doubt that it may not have worked. So tool validity and integrity of the tools is very important. And so you'll see toolkits like this. And something you might consider is like a field kit, or even if a kit for in-house is the connectors. So there's a copy of this image here. So we have things like a lot of storage media. This is a lot of extra media to write to. It could be large capacities, spinning drives, SSDs. SSDs would be great. They're going to cost more. Maybe just thumb drives, things like that. And then we have the tool itself. This is a tool that can be used to do multiple things. Some of these are simple tools, and I don't have all of them up, of course you can search, but they're simple read-only pass-through tools that have a sort of a kit of connectors. SATA, IDE, just you name it, different types of connectors here. You can't assume everyone's got the latest USB-C or so on. You might be done with older systems, and this course has a nice case with it. But yeah, there's a lot of things to consider when selecting the tools. This is a forensic imager, for example. This has multiple disks at one time. It can do multiple inputs, and it can wipe, format, do a blank check. So some of these tools will do this for you, and it'll do SATA, USB 3, PCI, and so on. So you can see, as well as network shares, which is a great thing too, is you can actually write to a network drive or server. So that's something you do within the in-house lab. But you can see this is a great desktop unit or even mobile. So now they're not cheap, of course. One could probably create one. Here's a more simpler kit, a Tableau Forensic SAS Bridge. So you could imagine the lab work for tool acquisition, tool maintenance, tool testing, and just the cost of these tools can be very great, but it is very important. So keep that in mind. So again, one of the things you want to consider also, so again, one of the biggest ones, of course, is the rules for data analysis. Again, always use a read-only, some way to do a read-only capture of the image. And that image itself, what format do you want to use? So a DD, for example, have a DD output, but there's proprietary formats, and there's an AFF format. So there's advantages, disadvantages of both. What you want to consider is where is this image going to be fed to? So you don't want to have to make a DD image and find out you got to convert it to some other image. Again, it's very timely, and the time itself can be a big impact. So capture the correct image that you need initially. So proprietary, again, there's advantages, disadvantages. Again, if you have the in-house tools and that's the format you use, capture, and you can capture it in that image, go straight to that image. Using, again, the read-only, hash verified sort of process here. So then there's AFF, for example, Advanced Forensics Format. It's an open source tool, open source image. There's advantages, disadvantages to both. SleuthKit, for example, will support it, which is great. Things like that. So knowing that you use SleuthKit, you might capture this in this format. So, and there's some good information. This is from the text. I'm not going to go through this here, but you can see there's a great methodology flowchart here. If the computer's on, yes, capture volatile data if needed. Turn the computer off. If possible, remove the hard drive. This is something that might be hard with newer laptops or things like a phone. We actually have disks that are actually on the board or even on the chip. So protect the device and acquire the data and have a contingency. and how that data is handled too. So when you create that image, maybe you put it to a SATA drive, external drive, or even just a thumb drive. You want to keep that in a tag and bag it. You want to keep it, keep the original one tagged and bagged if all possible. I say bagged. Think of ESD, electrostatic discharge. It's been sealed. It's been evidence. The chain of evidence, the custody chain, is all been sort of been handled correctly. Any faults in the system can again cause inadmissibility in court. So it's a very tight process. It needs to be followed. So again, we have some ways to different acquisition. We have logical and sparse, again, application layers, maybe a log file, file system layer. Again, and I think I mentioned this already, but this shows a good way to determine you might need to do with time being in essence. You might capture just a logical or sparse of just the home directory for the user, maybe just the email files. Again, using the same read-only method. Again, the right tools, I think I showed this already. They definitely should create a bitstream copy. That's what you want to have. Tools must be able to pass scientific peer reviews. You don't want any kind of, you bring into question, homebrew tools. And also the tool should log IO errors. This is a good one because if the tool has any read errors, you want to know about those. That might not affect the evidence, but that definitely is something you want to know. You want to keep those logs with the files for that case. So tool documentation, everything about the tool should be done correctly. So again, hash value. It's nice if the tool can create a hash value for you, and I'll show a demo of that here in a second. And of course, we want to make sure we sanitize the media, sanitize the media prior to copying data to it. So you still want to copy over existing image that has not been sanitized. So there are standards for sanitizing, and they're here. For us, the DoD 50, this DoD standard's a great one, and then the NIST SP 888 are two good ones to look at. I'm not gonna bring them up here, but realize you just don't grab off the shelf copy, buy it from Micro Center, an empty disk. You gotta make sure, even if it says it's empty, you want to make sure it's been sanitized properly, and you need to be able to prove it. So that's something very important here. And we're going to acquire our data. So I'm not going to go any more into that here. We're going to talk about some examples here. Again, the book itself, again, we'll look at the summary at the end here. So, but for now, let's take a look at probably the biggest ones we're going to see. Okay, thank you, Windows. One of the ones that this lab has you perform is something called DD. So it does actually work in Windows. I always say that in surprise because I use Linux a lot, so and definitely use it for here. But this has been around for a while. But you can see here the lab will have you copy over a DD file to your desktop. So this was done in the lab steps. And there's a d.exe and some sort of copyright text, but just an exe file. And opening a PowerShell with administrator rights. This is very important. We're dealing with disk level work in Linux and or Windows. You need to have admin rights. So I already went through the process of right-clicking on here and saying PowerShell admin, saying yes, allow it, and so on. You want to make sure you have admin rights for anything. In Linux, I did sudo, or make sure you have root access. So DD works basically in two ways. It's pretty straightforward. You have something called an IF, in file, and out file, OF. In file is just that. In this, I used the WMIC disk drive list, and I'll make a copy of this drive here, physical drive 0. So device ID equals, and there's the path. So in file is the path of that entire drive, and out file, I'll copy to the F drive, which is the empty drive I have available to copy to, and it's evidence.dd. And there's some options with DD. Look at the man page, look at the help files for those, size and progress. And you can see right now it's writing to a DD file, or it's attempting to write to this DD file here. So it says 0 byte size. So my guess is this will be updated when it's done. So on Ubuntu or Linux, same thing here. So here I have um, we have a copy of this read-only file. And here in my home directory, JSON, a file called the folder called read-only. Now the folder itself is read-write, but the links evidence file, of course, this is a read-only copy. So let's consider this has been done through one of those methods, maybe a read-only device. And again, we don't want to tamper with this. This is that original copy of this is the original copy from the actual evidence file. We want to maintain this also as read-only and create other copies from it. So you can see here, I already did this. I did sudo, which is super user do, and dd. We want to make sure we do this. Of course, I get the password for this lab. I think it's Tor. Again, we have in file and out file. Now, there's a lot of options. One of the biggest ones is called block size, or BS equals. Usually you can leave it off because DD will try to interrogate the drive architecture and see the block size as human use. But if need be, you might need to provide that. And then when we look at previous chapter, talked about disk size, block size in previous chapters. So there's ways to figure that out. But a lot of times the tools are great. They do this here. So this has already been done. You can see that we made an out file copy here in home JSON copy, and I call it evidence2.dd. Now this is an important thing here is this. Now you can see, well, great, the sizes are the same. We have an exact copy. Now, you always want to do a hash. So we can do an MD5 sum, and there's probably other. It's best to have several different options for this. MD5 sum home JSON read only. Let that run. That's going to sum the DD file. What we want to do is, there we go. We can see we have a sum of it here. There a little bit more. And then we want to go ahead and do one on the copy. Now, if the copy went great using DD, it should have no problems. But if any errors, if there's any kind of records, you should get an idea of the records and records out where there's no errors indicated in the output here. So chances are we have a good copy. But again, this is the type of thing you want to have documented in our sort of our notes, our case file, copies of the MD5 output, or MD5 or SHA1, and there's different ways you can perform this. There we go. And you see it matches. They are both exactly the same. So that's good. That means we have an exact forensic copy from that. Now there was other tools I talked about, and this one right here is one of them. This is the dcfldd tool. This is pretty. Here we go. So this is the Kali page for it. There's actually a home page for it also, which is a GitHub page. Kali page has some good things here we can look at. Hashing on the fly, this is great. You can actually tell it to do hashes for you automatically. It has disk wipes. So this is this is DD that's been sort of beefed up with some more capacity here. Now again, there's a lot of stuff here. Again, but in file, out file, using the where to write to. We can do patterns, but hash equals. This is a good one right here. We can actually send it a list of hashes to do. It's good to have multiple hashes also. MD5, SHA1, maybe 3 hashes at least. Some tools will do several hashes, and that's fine. You want to have multiple hashes if possible than just one to really prove that that is an exact copy of the evidence. There's all kinds of other stuff here too. So DDFLD, so we'll go and do that here. So here we're going to make a copy. It's very similar to what the DD command is here. So here we have DD, again sudo, but DD cfl DD, that's a mouthful there. And again, our in file is the from read-only folder, or read-only copy of this links evidence.dd file. We're going to make it one called evidence3. There's already evidence2 inside there. And we're going to pass in hash equals MD5 and SHA1. So we want to give it the password. We'll let that run. I probably could have done some stuff like status on off. Um, it gives you some status while it's doing anyways. You get some verbose output, but you can do write to a log, which is great. Um, write stuff to a log file. Save you some steps. And that's the thing is you like to save some steps if at all possible. Automate it, right? I'll do some automation. We'll let that right here while that runs. So again, some of these toolkits like this I showed you before do this. They do that. They actually have, and you'll see wipe drive format, do a blank check. That's fantastic. So you can see the value, even though it's very expensive. If your job is to, if your job is forensics, you're a forensics shop, the money you pay up front is going to pay you back in time. Because time is the one thing that is going to be a very, very hard asset. And you can gather time by having this do these for you and then make a copy of it for you of the evidence. That's fantastic. So it looks like we're done here. So you can see it's written records in, records out. We can see there is, I did an SHA1, and there's the MD5. And we can see it matches our previous MD5. Now, I don't have MD, this is not MD5, the source. It probably might be in the command line, but this MD5, the actual written out total MD5 was written out. You can see it matches MD5 of our source. So that again, that saves me some time. It copied and it created it for me. All right, so we'll wrap this up here. Take a look at the summary here. So again, there's a lot of information in this and some great examples of different things for both Mac. Here's MD5, some evidence. Mounting, unmounting, how to mount these DD files, things like that. So, and of course, the lab will have you walk through it. Key highlights, so of course, data acquisition of what it is, capture, and we have different captures, volatile, and static. And of course, you have sparse and full. So sparse or logical, or we have, of course, full disk. So again, time's going to be one of the essence here for that. Have contingencies in place in case something happens. My lab had just give me 15 minutes left. So when acquiring images from Windows, Linux, you need appropriate tools. Again, it's going to depend upon this your source or certain tools for the best for Linux or Mac. DDWorks use that in everything, so that's a great tool. And some of the things here that we should look at, which is talk about, of course, is I'm going to add in is after it's processed, it should be properly secured for electrostatic discharge and also tagged and tracked. And then that original copy should be locked away with only limited access. So we have or the actual drive itself. So we pull the drive from suspect system using the read-only toolkit we have, or field kit. We hashed it. We created a bit-by-bit copy, maybe to a server, or maybe to another drive. Then that original drive that came out of the suspect system should be tagged, sealed, signed, whatever, and bagged and locked away. And only we make more copies from that other copy that's been verified, and then verify those copies. So hashing is a key component. It gets used a lot in this process, and it is very critical. If you show that, for any reason, if you show that the copy you gathered evidence from does not match MD5 or SHA1, for example, of the original, you can also go and just not use that evidence or find a way to go back, make another copy, and verify that hash is correct. So, and the hashing goes a little deeper, which I won't go into here. I'm going to go into later. You can create hashes not just of images, but of files. Hash an image file, maybe it's a file image of someone holding evidence that is key in court. Of course, we have metadata about the file, but you also create hashes of files, Word documents. Anything can be hashed. So, but yeah, think about that there. How you approach the suspect system. Of course, what does your warrant allow you to collect? Things like that. There's a lot of variables to cite here, but focusing down to, you can see a very important thing, of course, is think about the collection, think about what kind of data you won't need, think about your tools, make sure it's read-only and hashed, and then only perform analysis on a forensics verified copy. I think that's probably the most important steps, things you can come out of this here. Plenty of tools you can look at, plenty of tools the lab will go over. But in any case, that is it. That wraps up our quick look at data acquisition and duplication. Thank you for watching.